Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. We are in section 11.5, and after the alternating series test, we will talk about absolute convergence and conditional convergence. So let us understand first, when we have a series, summation En, there is a corresponding series to this series, whose terms are the absolute values of the terms of the original series. So we can talk about another series, which is the absolute value of the terms of the series considered. So we will define now what we mean by absolutely convergent. Some series are absolutely convergent. When do we say that a series is absolutely convergent? If this series summation absolute value of an is convergent. If the series of absolute values is convergent. So, for example, this is a series. To find out whether this series is absolutely convergent or not, I consider the series summation absolute value of -1 to the power n-1 over n square. Now, if you take the absolute value, this will give you summation 1 over n square. And we know that 1 over n square is a convergent P series because P is equal to 2 greater than 1. For more about P series, please check section 11.3. So this is AN, and we found that summation absolute value of AN is convergent. So we conclude that summation AN is absolutely convergent. So this is simply the meaning of absolutely convergent. The series is absolutely convergent if summation of absolute value of AN is convergent. Now you may ask yourself, if the series is absolutely convergent, is it convergent? And the answer is yes. There is a theorem that says if the series is absolutely convergent, then it is convergent. So you can think of absolute convergence as a stronger type of convergence. So there are series that are convergent, and there are series that they are absolutely convergent. Absolutely convergent series are convergent series, but convergent series do not have to be absolutely convergent. I hope that this is clear. Let me give you an example. The alternating harmonic series. If this is AN, and if we consider summation absolute value of AN, this would be equal summation to 1 over n, which is the harmonic series. And the harmonic series, we have seen that it is divergent. So now this series is not absolutely convergent, but it is convergent because we have seen in the previous video using the alternating series test that the alternating harmonic series is convergent. So we have seen that summation AN is convergent by alternating series test. Bn is 1 over n, the limit is 0 and it is decreasing. Please check the previous video about alternating series test. So for this series, for the alternating harmonic series, the series itself is convergent, but the absolute value, sum of absolute value, is divergent. So this series is convergent, but not absolutely convergent. So what can you say about it? Well, we will give it a name. We will call it conditionally convergent. So if the series is convergent, but not absolutely convergent, then we will call it conditionally convergent. So you can say that the alternating harmonic series is conditionally convergent. And I will call conditionally convergent CC from now on, and absolutely convergent AC from now on. Okay? So you can say that there are three types of series. Series which is absolutely convergent, series which is conditionally convergent, and series which is divergent. And let us discuss this example. This is a series summation cosine n over n square. You need to notice that cosine 1, if you use the calculator and you are in the radian mode, cosine 1 is positive number, but cosine 2 is negative. Cosine 3 is negative. So this series is not alternating. It is not positive, negative, positive, negative. That's the alternating series. So you cannot use here the alternating series test. What can you do? This series does not have positive terms because cosine n sometimes positive, sometimes negative. You cannot use the integral test. You cannot use comparison test because these terms are not positive. Cosine 2 is negative, cosine 3 is negative. So what to do? Well, in this section, we have a method. Consider summation absolute value of cosine n over n square. Okay. And discuss the convergence and divergence of this series. Well, this would be absolute value of cosine n over n square because n square is positive. I don't know anything about cosine n because sometimes it's positive, sometimes it's negative, so I have to leave the absolute value here. Now, what to do? Now look to this series. This series now have positive terms because we have absolute value of cosine n. So all the terms are positive terms. So you can use comparison test, for example, to check the convergence of this theorem. I know that 1 over n square is convergent. And I know that absolute value of cosine n is less than 1 always. Okay, let us say less than or equal to 1. So if I divide by n square, and n square is positive, so I have this inequality. And I know that summation 1 over n square is a convergent P series with P equals to 2 greater than 1. So by direct comparison test, for more information, check section 11.4 about direct comparison test. What do we get? Summation absolute value of cosine n over n square is also convergent. So what is the conclusion? We found that this series is convergent. So what is the conclusion? If this is an, then summation an is absolutely convergent. All right. So this series is absolutely convergent. Another example, determine whether the series is absolutely convergent. Now we have two kinds of convergence, absolutely convergence and conditionally convergence. So he can give you any series and ask you to determine whether each of these series is absolutely convergent, conditionally convergent, or divergent. So for part A, if this is an, as usual, and let me consider summation absolute value of an. So that would be our strategy. Immediately, I consider summation absolute value of n. And this would be summation 1 over n cube. And I know that this is a convergent P series because P is 3 greater than 1. So what is the conclusion here? I conclude that the series summation an is absolutely convergent. Okay, so this is the first one. So the first series is absolutely convergent. What about the second series? Consider absolute value of an. Well, I'll have 1 over cube root of n. And I know that this series is divergent, P series, because P equals 1 over 3 less than 1. So what is the conclusion? The conclusion is series B in B, this series is not absolutely convergent. Well, is it convergent itself? Is it conditionally convergent? So now I need to consider this series. Summation an. How can I test this series for convergence or divergence? This is an alternating series. So this series is convergent by alternating series test. And why is that? Because limit bn when n goes to infinity is 0, and 1 over cube root of n plus 1 is less than 1 over cube root of n. So it is decreasing. So it satisfies the two conditions of the alternating series test. So this series is convergent, but it is not absolutely convergent. So the conclusion, this series is conditionally convergent. So this series is conditionally convergent. What about C? Let us consider this series. So I'll have n over 2n plus 1. Notice that now the terms are positive. N over 2n plus 1 is greater than 0 for all n greater than or equal to 1. So now I can use comparison test, limit comparison test as I wish. What is Bn here? Take the highest power, n over 2n. Oh, it would be half. So there is no Bn. So this means that if you take the limit of n over 2n plus 1, when n approaches infinity, you will get what? You will get half, and half is not 0. So by test for divergence, summation an, this series is divergent. All right. So this series also in C is not absolutely convergent. But let me consider the series itself. Is the series itself convergent? All right. It's an alternating series. And we have seen that limit of n, which is bn, when n approaches infinity, is half, not equal to 0. So this means that the limit of an, this is an, does not exist because it would be plus or minus half. So by test for divergence, summation an is divergent. So this series is divergent. It's not absolutely convergent first, and then we notice that itself is divergent. Some exercises determine whether the series is absolutely convergent, conditionally convergent, or divergent. Immediately we consider this is an, summation absolute value of n. It is 1 over 5n plus 1. Now these terms are positive. We have series with positive terms. I can compare this series with 1 over n. But 1 over 5n plus 1 is not greater than 1 over 5n. Actually, it is less than. And because 5n plus 1 is greater than 5n. So I cannot use the direct comparison test here. So I'll use the limit comparison test, where bn is 1 over n. And an is 1 over 5n plus 1. So limit an over bn. And for more about limit comparison test, check the previous section 11.4, the limit comparison test. When we divide the two, I'll have n over 5n plus 1. And the limit would be 1 over 5. And this is greater than 0. So by limit comparison test, an diverges, summation an diverges, which is, let me write, 1 over 5n plus 1 diverges. Since summation 1 over n is the divergent harmonic series. All right. So we have seen that this series is divergent. So what about this series itself? Summation an, where an now is the negative 1. So let me write it because here we mentioned an twice. So let us discuss this series. Well, this series is convergent by alternating series test, because limit of Bn, which is 1 over 5n plus 1 when n goes to infinity, is 0, and 1 over 5n plus 1 plus 1 is less than 1 over 5n plus 1 because the denominator is greater than the denominator. So it is decreasing. So Bn is decreasing and the limit is 0. So by alternating series test, this series is convergent. But it is not absolutely convergent. So the conclusion would be the series -1 to the power n over 5n plus 1 is conditionally convergent. So this series is conditionally convergent, and let an be this one. Okay, so I did not call this an. I didn't give it a name because I needed an somewhere else. All right. You have first you have to think of the series. Are the terms positive or not positive? If you put sine n 1, okay, you will find that sine n sometimes positive and sometimes negative. Sometimes sine sine 1, 2, 3 are positive, but sine 4 is negative. But if you multiply by 2, so let me discuss this. Sine n is a number that's greater between -1 and 1. We know that. But I have 2 sine n. And I have 1 now. So if I add 1, so this numerator 1 plus 2 sine n is a number between -1 and 3. So it could be positive sometimes, it's negative sometimes, it's not alternating. So I cannot use the alternating series test. And I cannot use all the tests, integral test, comparison test, limit comparison test, because the terms are not positive. So let me consider, as usual, the absolute value, if I call this an. So I will have absolute value of 1 plus 2 sine n. This is sometimes positive, sometimes negative, so I keep the absolute value. While here n cube is always positive because n starts from 1 to infinity. And now this series has positive terms. These are positive terms. I can use the comparison test if I like. We know that absolute value of 1 plus 2 sine n is less than 3. Okay, less than or equal to 3 from here. So if I divide by n cube, then this is less than or equal to 3 over n cube. But summation 1 over n cube is a multiple because of the 3. Multiple p series with p3 greater than 1. So it's convergent. So by direct comparison test, summation absolute value of an is convergent. So summation an is absolutely convergent. So this series is absolutely convergent. Let us consider immediately when n is always positive and we have -1 to the power n, so this is an alternating series. This series is an alternating series. If we consider absolute value of an, we will have 1 over ln n. Okay. Well, how to discuss now? These terms are positive terms. So use any test you like. But let me give you something here. Ln x is always less than x. Starting from 1, ln 1 is 0 less than 1, ln 2 is less than 2, ln 3 is less than 3. So this is a fact. And I can use this fact because ln n is less than n. So 1 over ln n would be greater than 1 over n. Notice that now I have positive terms. And 1 over ln n is greater than 1 over n. And summation 1 over n is divergent harmonic series. So by direct comparison test, summation 1 over ln n is convergent. So summation absolute value of an is convergent. So summation an is absolutely convergent. Sorry. Summation 1 over n is divergent. So how can you conclude that it is convergent? This is divergent. By direct comparison test, this theorem, this series is divergent, not convergent. So it's not absolutely convergent. Could it be conditionally convergent? Well, let us check summation an. Bn is 1 over ln n using the alternating series test. Limit of 1 over ln n when n goes to infinity, ln infinity, infinity, 1 over infinity is 0. We know that ln is an increasing function, so 1 over ln n plus 1 is less than 1 over ln n because ln n plus 1 is greater than ln n. So it's decreasing. So by alternating series test, summation an is convergent. So what is the conclusion? Summation an is conditionally convergent, or CC. Another example. What is cosine in pi? We have to understand what is cosine in pi. Well, if n is 1, I have cosine pi. If n is 2, cosine 2 pi. If n is 3, cosine 3 pi. If n is 4. What is pi, 2 pi, 3 pi, 4 pi? We know that cosine pi is negative 1. 3 pi, negative 1. So this is negative 1. This is 2 pi is 1. Oh, so this series is an alternating series. So cosine n pi actually is, you can write it as negative 1 to the power n, because if n is 1, you have negative, over 3n plus 2. So this is actually the series written in another form. Okay, let me consider, if this is an, let me consider absolute value of an. So this series, what do we know about this series? Now I have positive terms. So if you want to use the comparison test or whatever as you like. Of course, this is 1 over 3n plus 2. So I will compare it with 1 over n. I know that, or 1 over 3n. Okay, I know that 3n plus 2 is greater than 3n. So 1 over 3n plus 2 is less than 1 over 3n. But this doesn't help because I need it to be greater than divergent, not less than divergent. So using the direct comparison test is not possible here. So let us use the limit comparison test with bn equals 1n. And let us find limit an over bn when n approaches infinity. So again here, I'm not going to call this an. Okay, this is an in this case. This is summation an. So by an, I means 1 over 3n plus 2. When I divide by 1 over n, I will get n over 3n plus 2, and the limit would be 1 over 3 greater than 0. So by limit comparison test, summation an 1 over 3n plus 2 diverges because summation 1 over n is the divergent harmonic series. So now we know that this series is not absolutely convergent. Is it itself? Is it convergent itself? Okay. It is not absolutely convergent, but is it convergent itself? Well, it is an alternating series, so let us use the alternating series test. It's clear that it is convergent by alternating series test. Why is that? Since limit bn, which is this in this case, when n approaches infinity, is 0, because 1 over infinity is 0, and 1 over 3n plus 1 plus 2 is less than 1 over 3n plus 2 because this is greater than this. So it is decreasing. So by alternating series test, this series is convergent. So the conclusion would be this series is conditionally convergent. I hope it's clear and you understand now the difference between conditionally convergent and absolutely convergent series.